Okay, great. We'll then start. Sorry for the inconvenience, Mr. Bouchaud. It's a pleasure to have you today. My name is Reda. Everyone in the call here today already know me. I'm a physics undergrad from Belgium, the president and the co-founder of the Beta Sigma Club, which is a quant finance society. I also see that some of our friends from London and from Paris are in, because Beta Sigma has been a success in Belgium, and we will be expanding next year to London and to Paris, obviously.
So where are you located in Belgium?
I'm located I live near Brussels, but I study at the KU Leuven in Leuven.
Wait, I don't need this transcription, which is silly. Okay. And so I didn't exactly know what to expect in terms of student level and so on. So people are familiar with physics concepts, right?
Yeah, yeah. So everyone is an undergrad, masters. We have some PhDs. So and everyone is doing physics, engineering, mathematics. So you can go like on a good
Okay.
level.
Well, I try to prepare something
Great,
pretty
thank you.
general and not too technical. Should we wait a few more minutes or?
No, it's not necessary. No.
Okay. So I'll start sharing my screen so you can tell me if you get anything.
Yeah, we can see it.
Okay, so this didn't work. So let me find my slides. And maybe hide this. Okay. So you just tell me when you want me to go. You see my slides?
Yeah, it's perfect.
My door. Okay, well, good evening, everybody. It's very strange. Even after a few years, I can't get to terms with not seeing the audience, but that's the way it is. So I chose to illustrate some aspects of the application of statistical physics to financial markets with two topics, random matrix theory and endogenous dynamics, so that there will be two parts, and we'll see how far we go. But because I think maybe what's most interesting in general, I start with endogenous price jumps and self-referential feedback loops, and then we'll see how long I have to speak about the second topic. Okay, so let me start by showing a time series of the S&P 500 daily returns. And so what you see here is something that is intermittent. It's said to be intermittent. There are spikes of volatility that last for some time, and then periods of time where nothing much happens. This is actually a wavelet representation of the same time series, which, as if you're not familiar with wavelets, it won't tell you much. But essentially, this picture is saying that there's something self-similar about the motion of the S&P 500, which reminds physicists in particular of other phenomena like turbulence or other type of earthquakes, dynamics, and so on. But I'll come back to that in a while. So, just by eyeballing this graph, if price returns were Gaussian, if the prices were a geometric Brownian motion, which is the standard model for financial time series, it would look completely different. It would look like a well-mown grass, if you want, and so there wouldn't be all these structures. And so the basic so-called stylized facts of financial time series are fat tails in the return distribution. You see these spikes here due to price jumping from time to time, and actually prices jump a lot. And so the tail of the distribution of returns decays very slowly, not as a Gaussian, but as a power law, with an exponent mu here, which is pretty universal, actually, which is very robust when you change time period, when you change assets, and so on. The second thing that you see on this graph and that you can formally measure is the fact that volatility is a so-called long-range memory process. So spikes of volatility can last 10 minutes, but they can last 10 years. And so there's no intrinsic timescale in the way volatility in financial markets develop. There are two other stylized facts that are maybe well-known or less well-known. One is called the leverage effect, which means that there's a systematic correlation between returns and future volatility. Negative returns of the S&P tend to lead to increased volatility in the future. If you want, it's a kind of panic effect. When prices go down, markets become volatile and people trade more in a sense. And so this leads to enhanced volatility in the future. And then there's a more subtle effect, which is called now the zoom back effect, which is that when prices tend to trend either up or down, either sign, but they have a consistent direction of motion, if you want, then volatility in the future also increases. So the leverage effect is asymmetric when you change return to minus return, whereas the zoom back effect is symmetric when you change return to minus return, because trends can be up or down. It doesn't change the result. And so there are other stylized facts, more subtle ones, and related to maybe microstructure or multivariate statistics. There's a lot of them, and I won't talk about them all, but at least these four ones are extremely important, in particular for risk control and option pricing and so on. So what we need are models that encode these features that I talked about, these empirical features. They need to be encoded mathematically, and hopefully these models that can be written to try to model these effects, they're also asked to shed light on the mechanisms responsible for them, because it's one thing to describe with the model, it's another thing to predict with the model, and it's a third thing to have an understanding of what's going on. And I think that, at least for physicists, the most important part is understanding what's going on, because it helps building better models and having confidence on the quality of the mathematical models that one can build. It's always easy to build mathematical models that don't mean anything. So I think the search for meaning to equations is something that physicists are very wedded to. Okay, so as I said, prices jump a lot, and there are two lines of thought to explain why markets are so jumpy. One line of explanation, which is the standard theory in economics, is that markets are efficient and they essentially reflect fundamental value, even if it's hard to define fundamental value without referring to the market price, but that's another story. So in this in this picture, what makes markets jump is that there's a piece of unexpected news that becomes available and suddenly changes the fundamental value. But the problem is that there's a lot of jumps, as I'm going to explain in a second, that don't seem at all to be related to anything happening in the world. So there's another story that is picking some steam now, is what I call here the endogenous volatility story. And the idea is that it's not at all the fundamental changes that affect prices, but it's really the internal dynamics of the market itself, the self-exciting feedback loops that are, in some sense, essential to the way markets function, that leads to these jumps. So, of course, I'm not saying that some news that don't matter. Some news actually make prices jump a lot. But we also know from anecdotal evidence that all the flow, I mean, what people actually do without really any reason for that, is influential in prices as well. And I'll come back to that in a more precise manner in a second. So this is very much related to the well-known excess volatility puzzle in financial markets of Rob Shiller that was discussed since the beginning of the 80s. And essentially, just by looking at orders of magnitude, stock prices tend to fluctuate up and down on the order of 2% every day. And it's really hard to come up with a fundamental reason for such volatility. So the whole story of endogenous volatilities is strongly related to this well-known fact that markets seem to move much too much compared to what fundamentals would suggest. And here I'm showing a kind of archetype of such a scenario. This is the so-called flash crash in 2010, where the S&P went down like -9% in a matter of minutes with no real fundamental reasons. So this is a long standing puzzle, as I said, Schiller in the beginning of the 80s. Then there's another very important paper by Cutler, Potterba, and Summers in 1989, where they're trying to relate the large moves of the S&P or the US market in the 20th century with something happening in the world in the sense of making the headlines in the New York Times. And essentially, for example, this 1987 crash, -20% in a single day, well, there's not much of an explanation. Worry of over dollar decline and trade deficit, fear of US not supporting dollar, nothing really to explain such a huge drop in the S&P. And this one I like a lot too. No basic reason for the assault on prices, -6%. So what they conclude from this data set, which is not, as they say, it's 50 largest post-war movements, which is not a lot of statistics. But still, they say the evidence that large market moves occur on days without identifiable major news cast doubt on the view that price movements are fully explicable by news, which is, as I said, the standard efficient market hypothesis. So we've redone this analysis by improving statistics. For example, you can study price changes at the 1-minute resolution instead of looking at them at the daily scale. So already this increases the statistics a lot. But also instead of looking at the S&P 500, so the stock index, you can look at 300. We looked at 300 US stocks in the period 2015-2020. But actually, everything I'm going to say today is in agreement with a previous study that we had done with similar data, US stocks at the 1-minute bin resolution, but in 2008, so using data that was 10 years earlier than the ones we are using today, with no significant difference. So you can define a jump by a large event. So essentially, we chose as a threshold 4 sigma. So 4 sigma event shouldn't exist in the Gaussian world, by the way. So the sigma here is defined with respect to past volatility. So when local volatility is higher, it corresponds to larger jumps, and if past volatility is smaller, it corresponds to smaller jumps. So we scale the threshold, if you want, with the local measure of volatility, which is causal, which is always looking in the past. And at the same time, we synchronize the price time series with the Bloomberg newsfeed. So we're able to tag each news with a company name, and therefore know whether the jump is related to a news that appears in the Bloomberg newsfeed or not. And the first surprise is that a large majority of these 4 sigma events, 95% of them actually in this data set, occur without anything special happening in the newsfeed related to this company name. So there's a story here that has to be refined a little bit, because you could have stocks jumping, because of macro news, for example, but we've excluded that as well. So we are left with the idea that a lot of jumps seem to come out of nowhere. But what's more interesting is that if you now do some statistics on the profile, for example, the volatility profile of these jumps before the jump and after the jump, you find markedly different profiles. So let me explain what we find in pictures. So this is this is actually a single event, but of course the statistics is better if you average over all the news-induced jumps and over all the no news-induced jumps. And I recall here that news-induced jumps is a small minority of all jumps. Then essentially what you see is what I've shown here in the picture with the fit. The orange line is a fit that I'm going to explain a little later. So in a news case, well, by definition, before the news, nobody knew what was going to happen. The news is by definition something unexpected. So the profile is pretty flat, nothing happens. And then there's a big jump at the moment where the news comes out, and then the relaxation of volatility after the news. In the case where there's no news, then volatility seems to increase before the jump and decrease after the jump in a much more symmetric way. So that's interesting because it already suggests, even at the level of narratives, that indeed news occur out of a blue sky because there's nothing happening before the news, whereas no news jump seems to be related to a progressive increase of volatility before the jump and then a kind of final burst, which leads to this event that we tag as a jump. You can look at other types of statistics. I won't go into too much details, but for example, the liquidity in the order book is decreasing before the no news jump, whereas in the case of a news, and in particular in case of a news that is not scheduled, because or also in the case of news, you have to distinguish news that are scheduled, that people know they don't know what the news is going to be, but they know that some news is going to appear at, say, 2:30 European time, and so in this case, of course, you expect volatility to increase before the news, but I'm excluding these events here. So the summary of all this is that there's markedly different profiles in the two cases, which means that it's really two types of events that are fundamentally different in their dynamics. So the fit, these orange lines, they're fits that are suggested by what is called the Hawkes process, and I'll define that later more precisely. But essentially, if you believe in the Hawkes process framework, Hawkes process, as I'm going to say, are typical of self-exciting processes, then you can show that in the case where within this mathematical framework, in the case where the jump is due to an external news, which I've called here the efficient market class, because as I've said, in the efficient market theory, these jump induced by news are the only ones that are expected. Then what you expect is a flat line before the news, and then a parallel decay of this activity as t minus tj, where tj is the moment of the jump, to some power, and I'll go back to what is theta here, but essentially it's some value theta minus 1. Whereas the same theory also allows for endogenous jumps, jumps that are due to the self-induced feedback of the volatility on itself. And in this case, the model actually indeed predicts that jumps should be symmetric in their profile, with an exponent now which is not theta minus 1, but 2 theta minus 1. And what we found fitting the data is that indeed we could fit both the news case and the no news case with a unique value of theta, which is around 0.3. So this 0.3 is interesting because, as I'm going to show you, it is the same value, surprisingly, that appears in this describing an apparently completely different type of phenomena. But also remarkably, we see that the exponent theta and 2 theta minus 1 and 2 theta minus 1, this doubling of the theta here, appears to be well in line with empirical data. So the question will be, where do these endogenous jumps come from? And already this suggestion provided by the Hawkes fit is that it's due to self-fulfilling prophecies, in a way, self-exciting phenomena. But before moving there, I want to show you another context that's been studied by a group of physicists around Didier Sonnet a few years ago, where he studied events of the same type, but in a very different context. So this is, for example, the sales of books on Amazon. And in the case of book sales, you can have exogenous jumps due to the fact that, for example, the author appears on TV. And so the sales of the book is pretty flat before the interview and then goes up at the moment of the interview and then relaxes down. So this is clearly an exogenous shock, a news shock, if you want. But there's a lot of profiles in these Amazon data files where the amount of books sold is growing like this and then decaying back after the peak. And here there's nothing happening in the world. There's no, exactly as in the no news case, there's nothing except maybe a kind of word of mouth process that makes this increase and decrease of the sales. So sales and activity, or sales and volatility, can be thought of as a similar process. Here is the same story with YouTube views, and you see that in some cases when there's an announcement of a release of a YouTube video, there's a jump and then a relaxation. But in other cases, it seems that there's again a self-exciting process, a word of mouth, a crowd process that leads to an increase and a decrease that are much more symmetrical than these ones. And as I've said, in the paper of Sonnet et al., they've actually fitted these profiles exactly as we did too in the financial context, and found the same phenomenology. That is, some jumps are exogenous, some jumps are endogenous, and the very same value of theta, around 0.3, describing both the exogenous jumps and the endogenous jumps. So all this to say that there seems to be evidence that jumps in markets are really due to a crowd effect, are really due to some self-exciting processes. So let me now explain what Hawkes processes are for those of you who don't know. So Hawkes processes have been introduced in the context of earthquakes initially by Hawkes himself in the early 70s, and they've been applied to describe many self-exciting systems. For example, we know that crime or riots or bank defaults or, as I've said, financial activity, they seem to be self-exciting in the sense that when people join riots, it motivates other people to join riots and so on. So there's a kind of imitation effect that leads to this strange dynamics. So a Hawkes process mathematically is a Poisson process with a time-dependent rate. So lambda is the rate at which these events happen. But the peculiarity is that this time-dependent Poisson rate is related to the past activity of the process itself through this kernel. So DNS is 0 when nothing happens and is 1 when something happens. And you see that if something happens in the past at time s, then through this so-called kernel, it is going to increase the propensity of the market, the propensity of the earth, the crust of the earth, to have more activity in the future. So this is, in a sense, the simplest way to encapsulate this idea that the past is influencing the future through this self-exciting phenomenon. So something that's extremely important in this model is the so-called branching ratio, which is this object n here, which is the norm, if you want, of the kernel, the integral from 0 to infinity of phi of tau d tau. And n, if you want, the intuition behind n is, if you have an event, is this due to the exogenous drive, which is lambda infinity here, or is it due to an endogenous the self-excitation mechanism that I've described here? And so n is the probability that the event you observe is due to self-excitation. So if n is 0, there's no feedback. So the probability that the jump is, or the activity or the event is exogenous is 1, and the probability that it is endogenous is 0. But when n reaches the value 1, it means that everything nearly is due to endogenous effects. And when you fit this model on financial markets, you find two interesting phenomena that reminds us of critical phenomena of second order phase transitions in physics, is the fact that n is systematically very close to 1. And second, this kernel here is a power law in time, so no specific time scale, scale invariance. This scale invariance I've already mentioned several times, volatility scale invariance. Now we see again something that's scale invariant, which is this feedback mechanism. And here you recognize the exponent theta that I've talked about earlier. So within the framework of this simple Hawkes model, you can show that there are exogenous jumps due to lambda infinity. You can show that there are endogenous jumps due to the proximity of a critical point. And when you actually derive from the theory the shape of the activity in the vicinity of the jump, you find these results that I've already quoted, and in particular, this characteristic doubling of the exponent theta between exogenous and endogenous jumps. Okay, so all this is very good, and if you want more details on Hawkes processes, in particular in the financial context, I recommend this nice review paper here. Okay, so it seems that we have at least a mathematical framework, but this mathematical framework actually fails to account for several of the stylized facts that I mentioned in the beginning. If you remember, I talked about power law tails for the distribution of returns. This is not accounted for by this simple model. There's also something that physicists are very excited about, which is symmetry. And in particular, most models in finance, most mathematical models in finance, including Hawkes processes, are actually time reversal symmetric. I mean, it's not obvious because you have the impression here that as I'm writing this as explicitly as a coupling from past to present, that there will be a time asymmetry in the model. But actually, when you look more closely, you find that the dynamics of prices described by the Hawkes process is a time reversal invariance. That is, there's no way to detect the flow of time within the model. But if you look at financial data, you do see features that break this temporal reversal invariance. You are able, when you give me, if you give me a financial time series, I know what to measure that will detect whether you've given the time series in the right chronological order, or if you gave it to me in a reversed order. So we need a model to account for this time reversal invariance. And the way we have proposed to do this is to extend the Hawkes process to include not only activity. DNS is, whether something happens, for example, whether there's a trade or not in the financial market at time S, but also price changes. And I think it's very intuitive that traders, the way traders, behave and affect this rate of activity is related to the activity itself, fine, but it's also related to what the price has done. And here, what is important is to have both a linear coupling and a quadratic coupling. The linear coupling describes what I've told you as called the leverage effect, which is, as I said, is the fact that negative price changes seem to increase volatility. So L would be negative here. Negative price changes lead to an increase of future activity. And hidden here, and of course, this would require a little more time to explain, but here we encapsulate the zoom back effect. We encapsulate the fact that when the past prices have trended up or trended down, then again, future activity is going to increase. So this is a very interesting model because when it's calibrated on data, so okay, I'm skipping a little bit the details, but what you should take out of this slide is that it is relatively easy to calibrate such a model on price changes. And what you find is that you are able, a little bit by construction, to reproduce the zoom back effect, which is related to time reversal invariance violation. But more importantly, by calibrating the model on activity alone, that is determining this K matrix here that is involved in the quadratic term in the Hawkes model, you're able to go from um, parallel to non-exponential tails, thin tails in the Hawkes case, to fat tails in the quadratic Hawkes model. So what I'm showing here is, you remember I told you that returns on the x-axis here, log returns actually, are parallel distributed. This is a cumulative distribution of jump sizes. And so what you see here, this tail here, the black line is data, is between x to the -3 and x to the -4. These are the two slopes that you see here. So this is the very first stylized fact that I talked about. Whereas Hawkes processes would lead to this very thin tail decaying exponentially fast. And if you calibrate this quadratic Hawkes model, then without calibrating it on price changes itself, of course, that would be too easy. But by calibrating it on something else, on correlation of activity, essentially, you're able to reproduce, this is the blue line, parallel tails in the distribution of prices. So what I'm saying is that at least at the level of mathematics, if you want, this is a model that seems to capture a lot of the stylized facts that I've alluded to at the beginning, and also allows to understand this coexistence of endogenous jumps and exogenous jumps. So to do a little more on that front, and this is going to be maybe a little fast and abstract for many of you, but here up to now, I've implicitly spoken about lambda being the rate of activity without defining really what the activity was. So let's think of activity as trades, or activity as price changes. Every time there's a trade, DNS is equal to 1, or every time there's a price change, a midpoint change, there's a DNS that is equal to 1 and 0 otherwise. But you can define activity in financial markets in a much more detailed way if you look at not only the price, but the full order book. That is the full list of orders that are in the order book. And as you know, there are three types of events if you look at the microstructure of markets. One is market orders, people wanting to buy immediately and sending a market order. Limit orders, also called passive orders. So orders that are placed in the book and that wait until execution, and cancellations. So if you restrict to the best two limits of the order book, you have 3 types of events per side. And because there are 2 sides, you have actually 6 types of events of which you can follow the activity. So there's a 6-dimensional vector, lambda, which describes the rate of these 3 times 2 types of events. Actually, all the statistics in financial markets is very symmetric when you look at, bid prices and ask prices, that is prices to buy or prices to orders to buy or orders to sell. So it is a 6-dimensional vector. By symmetry, you can reduce the calibration problem to a smaller space. And so extending this Hawkes model that I've talked about to this 6-dimensional vector, then you have objects that are much more complicated. For example, the phi kernel of the Hawkes model is actually now a 6x6 matrix, because DNS is a 6 vector describing, again, the activity, market order, limit order, cancellation, both at the bid and at the ask. So you need a 6x6 matrix to relate a 6 vector to a 6 vector. And this leverage kernel is a 6 vector, and this quadratic Hawkes kernel is also a 6 vector. Anyway, it's a big model, but as you probably also know, with high frequency data, there's a huge amount of data. I mean, these market orders, limit orders, cancellation, they happen on the scale of sometimes milliseconds or sub-seconds anyway. So there's a lot of data to play with, enough to calibrate all these things. And what you find in the end, and I won't go in the details of the calibration exercise, and I won't even show you the shape of these objects, but what I'm aiming at here is that in the end, what you find is that all these feedback kernels, they say something very simple. They say that if prices have trended in the past, or if volatility was higher in the past, then the effect on the event rates net is to decrease the volume in the order book. So if there was increased volatility for whatever reason in the past, there will be more cancellation and more market orders than limit orders. And therefore, the order book, the liquidity provided to the market is going to decrease when there is an increase in volatility in the past. But you see, that's something very interesting because it suggests a destabilizing feedback loop. If there's less volatility, if there's less liquidity in the order book, it means that the market is more fragile, and therefore it might lead to an increase of volatility, which will again decrease the volume in the order book and so on. So that's what I've explained here. Volatility increasing means liquidity decreasing, and this leads to potentially a further increase of volatility that again will lead to a decrease of liquidity. So if you put that in a model, in this type of Hawkes process model, then what you find is that as a function of the feedback strength, here is you can forget about this axis. It's the inverse memory time of the kernels, but it doesn't matter. What you find is that there's a phase, there's a region of parameters where the order book is stable. This is numerical simulation. This is within the model. Of course, this is not market data directly. This is to have a clean toy model to see what's going to happen if you have such a feedback loop. So there's a strength below which there's no liquidity crisis. That is, there's always some volume in the order book. But then beyond some threshold, you enter a regime where the market is unstable in the sense that there will be events where the order book completely empties out, which leads to a crash. So this is an example within the model, again, of the spread dynamics. The spread is the difference between the bid and the ask. And so you see that around this critical region, the spread is quiet, is stable, but suddenly there's this big increase and then a relaxation to a stable spread again. So we've analyzed this using the tools of statistical physics, in particular the critical scaling, finite size scaling tools, and we found that this within the model, this is really a second order phase transition that physicists and statistical physicists know a lot about, although we haven't been able to do much on the front of explaining analytically the value of the exponents, and we haven't solved the model in a sense. We have a numerical simulation showing that there is something happening which is interesting, but we've not able to completely understand what's going on. So as a conclusion of the first part, well, as I've said, the excess volatility puzzle and everything I've shown you suggests that markets, and actually the same is true for economies as a whole, markets undergo turbulent endogenous dynamics, very far from the rational equilibrium or efficient market hypothesis. But of course, going to this in more details would be another talk. So if it is not fundamentals driving prices, it must be flows, it must be what people do. And there's a lot of activity in that direction currently, in particular, for those of you who haven't read this paper by Gabex and Koigen, there's what they call the inelastic market hypothesis. I also have a paper following up on their idea that formalized the idea that flows are actually dominant in determining price moves. So if you want, what you want to predict when you want to predict prices is not necessarily to predict fundamentals, because this is a subleading effect. What you really want to predict is what other people are going to do. And whatever they do, for whatever reason they do it, they're going to impact prices, and that's going to be the main reason of volatility. Of course, this is a very heterodox view of markets, and it's far from being a consensus in the economic literature. But this is, after 30 years of looking at markets every day nearly, this for me has become an obvious conclusion. So I've described quadratic Hawkes processes as a convenient unifying framework. But of course, as I've said, there's still a lot to be done, in particular to explain this phase diagram. So I see I have 15 minutes left. I don't know if you want me to go into the second part, or if you want me to stop and to take questions and to engage in the discussion. That's really up to you.
The time available is really your time available. So if you have some extra time to go over parts two, like feel free to. Thanks.
Okay. Are there any questions?
I don't have yet. Let's go.
Okay.
Yeah. I wanted to ask you, how do you calibrate Hawkes processes, especially Q Hawkes processing?
So this requires a little bit more of mathematics, but essentially what you can show from this type of specification of the model is that you can find measurable correlation functions between activity and past prices. You can find enough of these correlations to determine, through what's called Walker equations that you can invert numerically, you can relate unobservable directly kernels like these ones that you assume exist, but they're not immediately available to you, to objects that are available to you, which are these correlation functions. So this is explained in our papers. And this is the way, for example, we've obtained these curves here for the various kernels.
Okay, thank you.
Of course, it's more complicated in the case where you have bigger objects, but essentially it's the same logic. There are more indices, but in the end, it's also relating observable correlation functions to these kernels. Okay, so let's now move to another topic that's close to the heart of physicists and of course also people in probability theory, which is random matrix theory. So since more or less all of you, I guess, know about finance, everybody knows about the famous Markowitz optimal portfolio formula that gives the composition of a portfolio in terms of the weight of this is a vector of the weight of the different assets you should put in the portfolio. In terms of the predicted gains, this is a vector as well. And this is the inverse covariance matrix or correlation matrix, depending on how things are normalized. And so to apply this formula, of course, you need to have some information about covariances. And this is really because risk is not only volatility, but it's also correlation. So volatility is a list of n numbers if you have n assets, and correlation is an n by n matrix, which is symmetric, but still it's a large object. So correlation is important because if you're able to invest in decorrelated products, then it reduces vol. So that's essentially the content of the Markowitz formula. Another way to see that both volatility and correlation is important is that when you look at the S&P 500 volatility, when it increases, it's actually both due to the fact that single stocks in the S&P become more volatile, but roughly equally, the correlation between all these stocks increases as well. So when there's a spike of the VIX, if you want, if there's a spike of the volatility of the market, it's not only due to the fact that each stock becomes more volatile, it's actually due to the fact that stocks become more correlated as well. Everything's tend to move in sync when you are in a crisis mode. So, as I said, risk is really volatility and correlation. And the problem of that is that when volatility is relatively easy to predict, at least to measure, there are option markets that help calibrating the volatility of each instrument. Correlations is much harder, in particular because of this dimensionality problem, because the fact that if you have 500 stocks in the S&P 500, then this is a huge object of size 500 times 499 divided by 2. So there's a lot of coefficients to be calibrated. And if you miss the evolution of the correlations, even if you have a very good model to predict what volatility is going to do, then if you miss the evolution of correlations, you might completely miss the realized risk in the future, the out of sample realized risk. So it is really a very important problem to understand how to model both volatility on the one hand and covariance on the other. So maybe I'm going to go a little quickly on that. This is just explaining in words what the Markowitz equation means. It means essentially that you should allocate more on modes, that is eigenvectors of the covariance matrix, if you want, that correspond to small eigenvalues. And so, you over allocate on things that you feel are less risky and under allocate on things that are more risky. But again, this is assuming that the covariance structure is fixed in time, because otherwise things that you believe to be less risky in the past might very well become very risky in the future. So if there's a shift of the covariance matrix, if there are rotations of these eigenvectors, you might be in trouble. So if we come back to the question of calibrating this covariance matrix, there's now a pretty well-known story, which is that if you have large matrices and not enough data, then the problem is very ill-defined in the sense that the empirical covariance matrix is going to be very different from the true covariance matrix. So what I'm going to say here is, first, assume that the world is stationary. Assume that there is an underlying process that is the same tomorrow as it was yesterday, is the same in the next 10 years than it was in the last 10 years. Of course, this is not true, but let's put ourselves in the best case scenario, in a sense. Then what is problematic is that when the number of assets here, 500, is large, then in order to pin down this covariance matrix, again, assuming it's stationary in time, requires the number of data points. T is the length of the time series that you have. So you observe, for example, 500 stocks over 4 years. This will give 1,000 daily returns. And from these 1,000 daily returns, you have to construct the 500 times 499 divided by 2 pairwise correlation coefficient. And what we know now from random matrix theory is that in this case, when T is not very, very large compared to N, the empirical correlation matrix is very different from the true one, as I've said. So for example, imagine that the true covariance matrix or correlation matrix is just the identity matrix, so no structure whatsoever. In this case, you expect that all the eigenvalues of the covariance matrix are equal to 1, because the identity matrix, is diagonal and has all elements equal to 1. So this is the spectrum that you expect. The spectrum of eigenvalues should be a delta function at 1. But if you try to measure that on data, so if you generate uncorrelated time series and measure the empirical matrix on this time series of length t, then what you find is a spectrum that is actually not at all a delta peak at 1. It's here I've shown what happens when the ratio of n over t is equal to 0.5. This is the dotted green line, or 0.25, which is the dotted red line. So you see that as Q decreases, it means that you have more data for a given n, and so you expect that these empirical lines here should shrink towards the blue line. But you see that even having 4 times as much time steps than you have data, then you have assets, sorry. So here in my example, n over t is 0.5, sorry. But even if you had 0.25, you see that you're very, very far from the asymptotic result. So what it means that in practice, there's no way to determine the empirical covariance matrix. You're never in a regime for large portfolios. You're never in a regime where T is extremely large compared to Q and allows you to recover the ground truth. And of course, things are even worse in the case where the world is not stationary. So let me, because I don't have much time now, so let me really go very fast on the messages I wanted to convey. Well, first of all, random matrix theory provides you with tools to optimally clean the empirical determination of a covariance matrix and be as close as possible to the ground truth when we know that noise effects are important. So how to get rid optimally of this noise? As I said, in principle, you should get the blue line, and in practice, you get the red line, for example. But there are ways to somehow get closer to the blue line, and that's what the recent ideas in random matrix theory have provided. So I'm going to skip over that. The only thing I want now to convey as a message is that random matrix theory allows you to do something even better, which is to detect the changes of the true covariance matrix underlying your process. As I said, there's no reason to expect that the covariance matrix that was ruling the markets in the last 10 years is going to be the same as the one in the future for several reasons. One is that, for example, companies might diversify their activity, and therefore the true correlation between two stocks might change because, I don't know, Pepsi might start selling beer and Coca-Cola still hangs to the old recipe. I mean, these things can happen. But what is amazing with random matrix theory is that you actually don't need to know the underlying true structure of correlation to be able to detect that it changes. And so that's the miracle that I don't have time to explain, but there's a kind of large dimension miracle, a kind of central limit theorem miracle, if you want, that allows you to detect non-stationarity, even if you don't know the true structure of the market. And so this is, for example, a graph that shows you that even if you don't know anything about the underlying structure, the overlap between the eigenvector of a first period with the eigenvectors of the second period, they should be described if the world was stationary by the red line. Even if you don't know what the world is, you know that this red line should hold. And empirically, instead of having the red line, you see these green points, which are below the red line. And so this allows you to know for sure that the structure of the correlation was not the same in the first, in the second period. Again, even if you don't know what the true covariance matrix is, because as I said, it's impossible to measure, you know that it has changed. So that was what I wanted to convey in the second part of the talk. And again, at the end, I wanted to explain how statistical mechanics type of ideas could explain how correlations can jump from one value to a different value in a matter of a few days. But I'll skip that and conclude by saying that I've focused on two specific applications of statistical physics to finance, but there's a lot of activity on other topics, and I'm listing a few here, in particular in the modeling of supply chain and input-output networks. There's also a lot of work on agent-based models, and the main idea here is that by adopting a point of view closer to statistical physics, then you can have things like surprises, phase transitions, surprises at the macro level that appear from simple micro elements. And as we know, this happens all the time. This is water at 0 degree, and we know that by changing the temperature by a minute amount, you change water from being a blue liquid to a white solid, and this is without changing anything at the micro level. I mean, this is the same H2O molecules, and still something completely different happens at the macro level. So I think that there's a lot of examples that could be rationalized within this type of ideas in markets and in macroeconomics. I gave the example of liquidity crisis, but I think more generally, crisis might be understood in the same using similar language. So I've given here a few references, in particular on the second part, which I thought I would not have time to go through if you're interested in more details. So I hope this was useful. And as I said, if you have questions, I'm happy to stay for a few more minutes.
Thank you a lot, Mr. Bouchaud. It was really interesting. Yeah, if someone has questions, just raise your hand and ask it. Yeah, Dietmar, go on.
Thank you for the interesting talk. I had a question, maybe not related to the topics of this evening, but when doing some reading for my master thesis, I came across a paper of yours from quite some time ago on the phenomenology of the interest rates curve.
Yes.
And I was, you talked a bit about modeling the interest rate curve as some type of stochastic string.
Yes.
And I was wondering how you look back at that type of description after quite some time, now that a lot has changed with respect to interest rates that became negative and so on. And if you still think that model like a stochastic string or even a stochastic field is something relevant or could be looked at in more detail.
So we haven't redone the statistical analysis that we had done at the time, and I think it would be extremely interesting to redo these analysis and see how things have changed. Indeed, I'm ready to bet that some of the stylized facts that we found back then are still true today. In particular, how the volatility of the interest rate, the forward rates, behave as a function of maturity of horizon. But of course, this needs to be rechecked. On the other hand, I think that the idea that the interest rate curve is a string with each point, in a sense, anchored to the point before and the point after, so there's the kind of elasticity of the curve, is something that I think is going to be still the case now, because this seems to be intrinsic to the fact that the interest rate curve is a curve. I mean, it can't disintegrate and have rates all over the place at too nearby maturity. So, as I said, we haven't redone this analysis, and actually, I'm happy you know this paper, because when we published these papers 20 years ago, we were pretty happy with them and thought that they would have some impact. And unfortunately, as happens very often in science, what you believe to be interesting is not necessarily what other people find interesting. So this is a nice example of something that we were very happy with and jumping around, thinking that we had done something interesting, and that actually was a flop. I mean, nobody really picked it up. So if someone revisits these ideas 20 years later, that would be great.
Okay, thank you. I thought it was an interesting paper, nevertheless.
Okay, thank you.
Okay, Clémence. Yeah, so Clément has a question in the chat, so I will read it out loud. So his question is, don't you think there is a Bouchaud effect on the market? Do you see some of your published ideas being incorporated in the market in terms of alpha decay, for example?
This is very hard to say, because in terms of alpha, we don't publish anything. So as you know, I mean, there's part of my activity that is academic and part which is professional and related to CFM's funds. And so everything that we believe is related to, predicting the direction of the market or the direction of assets, we never publish them. Or when we publish them, they are related to kind of well-known effects like trend following. And if you take that particular example, by the way, it's very striking that trend following has lasted has been present for the last 200 years. We've published a paper on that in 2014, showing that the trend following is very consistent over 2 centuries. And even after publishing this, trend following is still working. So I think there are effects that are so ingrained in human behavior that they're not going to go away. I think, trending is something that humans cannot resist. And so this effect will not go away, that's for sure. So on things that we publish, I think it's very difficult to see anything statistically significant, because, for example, when you publish about random matrix theory, this gives people a better way to measure correlation matrices or things like that. And what would be the effect of that in financial markets? It's not clear, because, well, for one thing, there's only a very small fraction of the whole financial industry that is interested in what we're writing about. So I'm not expecting a big effect there. Another example is things that we've written on option markets. We've written about discrepancies between option prices and what we believe to be good pricing models. And these anomalies, if you want to call them that way, they still exist after 20 years. So in the end, I think that you have to be, you have to come up with a paper on something that's extremely strong and extremely obvious for other people to take notice and trade on these ideas. That's what I think. Even if maybe some of our competitors use our paper, and I've been told that this happens sometimes, I don't think it has a crucial effect on the way markets behave.
Okay, thank you. Maybe, yeah, I don't know how much time you have left, Mr. Bouchaud.
Maybe 5 more minutes?
Yeah, let's do then a last question. Emile?
Yes, can you hear me?
Yes.
Yeah, first of all, thank you for the excellent talk. I wanted to know maybe a little bit more about the link between rough volatility and your approach. I think it was mentioned on one slide, the approach
Yes.
by Professor Gattrell. So is there a link between like the theta that you're using, like the scaling property and the monofractal scaling of log volatility? Is there a similar intuitive like interpretation, like log volatility scaling, not with a square root law like everyone uses, but sometimes markets are more rough, sometimes it's more smooth, so the 0.5 or what is it, the Hurst exponent could be higher or lower depending on the market regime. Is there a similar type of interpretation, or can you just elaborate about the link?
So that's a very good question, and there's a lot that's been written on this by Mathieu Rosenbaum himself. So I think if you're interested in detailed links between quadratic Hawkes processes and rough volatility, you should read their papers. I mean the papers of Mathieu Rosenbaum. I think that essentially the content, the underlying content of the rough volatility model is partly captured by Hawkes processes, but not completely. I think although Mathieu would say that he explains everything in terms of Hawkes processes, I think it's not entirely true. I think there's subtleties that are not completely understood in the link between all these approaches, and I think from an academic point of view, at least, trying to find a really unifying theory that in details explains how rough volatility appears from feedback effects, from the type of feedback loops that I've talked about that are encapsulated by the Hawkes process, is in my view a very interesting and fundamental question. We see that things seem to be similar and related, and there are tantalizing links, but to be very precise about those links is still a little bit out of reach.
Okay, thank you.
There's also, if you're interested, there's also a recent paper by Julien Guillon on path-dependent volatility, which on some aspects are deeply related to the quadratic Hawkes model that I've presented. So there are various points of views that are similar but different, and we are not yet at the level of a kind of grand unification.
Okay, thank you. Then we will wrap up this event. Thanks a lot, Mr. Bouchaud. It was a pleasure to have you today.
Thank you for the invitation, and I'm sorry for the
no
glitch.
worries, no worries. We are all